In this section, our topic is alternating series test. Big difference between this section and the previous ones is that in previous sections, 3 and 4, we assume that the members of our series are all non-negative. This is the first time where we'll analyze the series where the members might be positive as well as negative, although in a very special way when the members of the series alternate, like one positive, negative, or the other way around. So for example, I know 7 minus 3, 5, negative 2. Of course, this will diverge because of the divergence test, because numbers are too big. But let's say 7 over 1 minus 3 over 2, 5 over 3, negative 2 over 4. Now I'm doing better. And then next one, so 1 positive, 1 negative, 1 positive, 1 negative. That's called alternating series test. A general form of those tests is actually this one. So we'll analyze it in the following form. We'll write it as sigma n goes from 1 to and then negative 1 to the n plus 1 an, where an is non-negative. So generally an itself is assumed to be non-negative or positive most often. And then alteration of the sign is obtained with this member negative 1 to the n plus 1. Why? Because when n is 1, you will get negative 1 squared, which is 1. That makes it positive. But when n equals 2, you will get minus 1 to the 3, which is negative 1. So generally, you will get even exponents, which makes it positive, and then odd exponent makes it negative, and so on and so on. So here's the main theorem. And that is actually alternating series test. In certain situations where everything is nice, then we can make a conclusion about the convergence of this type of alternating series. So, if an is greater or equal to 0, that's what we said usually, then a limit of an is 0. I say, of course, because we know divergence test. But also, and the sequence an is decreasing. Is it decreasing or non-decreasing? Non-decreasing. So is decreasing, which means an plus 1 is less than or equal. So every next member is less than or equal a, and technically I should call this non-increasing, but I think that would confuse you more than just if we say decreasing. Then sum n goes 1 to infinity minus 1 to the n plus 1 an converges. By the way, people very often call this test a Leibniz test because German mathematician Wilhelm Leibniz was kind of first one that noticed how this test works, or at least it's attributed to his name. I never checked the history why exactly his name was attached to it. So let's see the reason for the proof, and actually it might, this also might tell us what's happening here. So here's the proof. We'll analyze separately our partial sums where the index is even from those when the index is odd. So let me consider S to n. So what would that be? A1 goes with the plus, minus A2, plus what? A3, minus A4, plus A2 and minus 1, minus A2n. then what? Let's consider these as one member. So basically this looks like a partial sum of a series, but not the two nth. So I'll call this B1, I'll call this B2, I'll call this Bn. But now what? Each of them is greater than or equal to 0. Why? Here is where it's crucial that here is where it's crucial that that all these that we have a decreasing sequence. So A1 is greater or equal to A2, so the difference is non-negative. The same thing here, the same thing here. So they are all non-negative. So now I can apply our knowledge from before. So what happens then? I have the following. I know that then S2n is increasing sequence. Why do I know that it's increasing? Because the bigger n, I'm getting more and more positive members or non-negative members, so definitely increasing, or at the worst non-decreasing. But what else do I know? Now I will rearrange it a little differently to give me some other information, and that is that S2n I'll keep first, and then I'll group the other two like this. And so on. So I'll group even first and then odd. But what happens here? This is now negative because negative one dominates because that's bigger. This is negative or not positive for sure. This is negative. So what do we have here? To A1 we are adding some negative numbers, or at least not positive. So what will that do? It cannot make A1 bigger. This will be less than or equal A1. And now if you remember that big theorem from section 9.1, this sequence S2n is increasing. Okay. Oh, by the way, the comment here I need from the previous line that S2n is greater or equal to 0. So my S2n is increasing and it's bounded. It's greater or equal to 0 and less than or equal to A1. So if a sequence is increasing or monotone and bounded, then the limit exists from 9.1. So limit S2n when n goes to infinity, I'll call it S1, exists. All right. What happens if I have S2n plus 1? So if I cut off odd number of members, basically what I'll do there, I will treat it somewhat like this here. So it will be A1 minus A2 plus A3 minus A4 plus A5 minus the last one on the minus will be minus A2n and plus A2n plus 1. And then what? Now I will group them like this, like a minute ago. And what happens? A1 is positive, leave it on the side. Then these numbers are less than or equal to 0. So what will that tell you? It will tell you basically that the longer I go, the more negative I accumulate. So S2n plus 1 is decreasing. What else? I also know not only that it's decreasing, since I'm chipping off from A1 the same way as before, I know that S2n plus 1 is less than or equal to A1 and greater or equal to 0. So what is that telling you? It's telling you for the same reason that limit of s to n plus 1 when n goes to infinity exists. But I'm not sure if that's the same limit as the one that I got a minute ago, so that's what I'll call it s2. So both limits exist. Generally, those even ones go bigger and bigger, like this. Those odd ones go smaller and smaller. They both have their limits, but either the same limits or they stay apart. Generally, it's very easy to conclude what's happening. We know that s to n plus 1 equals s to n plus just one member, the last one, a to n plus 1. If we take a limit, when n goes to infinity, and here is the crucial assumption that limit of an is 0, so this approach is 0. So what is that telling you then? This limit we call s2. Odd ones, yes. This one we call s1 plus 0. So they are the same ones. So generally, whether n is even or odd, all these partial sums converge to the same one. So that's why the limit of Sn for any n, so this is here, limit Sn when n goes to infinity exists, and it's equal to that s, which is the same as s1 and s2. So okay, it is. Actually, what was it necessary to see this proof? I think we learned a lot. This game of rearranging, first seeing them like positive and then dominating next negative, or the other way around, keeping first one aside and doing it the other way around, is actually quite an important technique here. So let's practice this and then practice how to estimate the error. That's what we started last time, and that's actually the whole section. It's not that complicated. So here is the one example. Analyze the following series, sorry, 1 to infinity, negative 1 to the n plus 1 over n. That's the famous Leibniz series. So what will that be? 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and so on. So what do we have here? An is just 1 over n. So just positive part, absolute value. So what do we know? An is decreasing. That's obvious, I don't need derivatives like that. The bigger n, the smaller the fraction. What else? The limit an, when n goes to infinity, is 0. So what do we conclude? That the series converges. That's it. All right, now the question is, can we calculate the sum? In this case, yes, but very often we cannot calculate the sum again. We address the question of what is our error if we cut it off too early. So let's say, or shall I do this? Yeah. Let me calculate. So, what is the error if we take that our sum is approximately S10? So if we just take first 10 members, so what is S10? 1 minus 1 half plus 1/3 minus, and the last one will be minus 1 over 10. And when you calculate that, approximately you will get 0.64563. My question is that correct? No, it's not. We are a little bit off My question is by how much? How much can we guarantee our result? And actually it's quite clear. So when we cut it at S10, we get the error R10, that's S minus S10. So how much did we lose when we cut it off? So generally what? This is 1 over 11 minus 1 over 12 plus 1 over 13 minus 1 over 14 and so on. And then that pairing from a minute ago will help us to estimate this. Why is that? Skip the first one like a minute ago. Take this pair, and all these pairs. So what would happen? Obviously, since the first omitted, so what can I conclude? Actually, maybe I rushed this a little bit. It's okay. Maybe I should have done it the other way around, the argument. If you look at this, what can I say here? Each of those members that I omitted is a negative, do you agree? So generally, they would chip off from this 1 over 11. So my error is 1 over 11 and a little less, so definitely my error is less than or equal to 1 over 11. And we say here, the error is always less than or equal the first omitted member. First omitted member is 1 over 11, and that's what it is. But the error in this case, because the first coming member is positive, R10 is greater or equal to 0. Why? Because then if we rearrange it like this, pair big and then small, big and small, then obviously each of them is not negative, so it's greater than 0. So when your first omitted member is positive, your error is positive, but less than that omitted member. What if I were S minus S11? My first omitted member is negative, so basically I would do the overestimate, and my error would be again less than 1 over 12. So that's what changes. All right, and that's the theorem about alternating series remainder. Let me warn you about something, and I'm not going to insist on that too much, but you'll have a couple of homework problems like that. Very often we think of the sum of these infinite sums like sums. So you want to use commutative law, you want to do associative law, distributive law, and everything. Actually, commutative law has to be used very carefully. Why? Because these are not really sums. There is a limit there, and that limit doesn't support all the operations. So generally, you can see in one of the examples that actually if you have alternating series, sometimes it converges, sometimes. Even if it converges, when you reshuffle the member, if they go too far, then you can change the sum dramatically. So you have to be careful how you use commutative law on sequences, on series where the members change sign. So it has to be done more carefully. As I said, look at a couple of homework problems at the end of your section that illustrated that. All right. Here is one very important concept actually connecting this section with the previous one, and that one is called absolute convergence. So definition. The series sum a and n equals 1 to infinity is called absolutely convergent. If the series consisting of absolute values converges. Even the way we code it, it looks like when the question is here, okay, if the series of absolute values converges, does it necessarily mean that the original series must converge? The way it was formulated, it's absolutely convergent. It looks like yes, and the answer is really yes. So theorem. If sum of absolute value and n equals 1 to infinity converges. then sum of the A and when n goes to infinity also converges. When this gets established, I want you to think of absolute convergence like a super convergence. So it's, you say more than just saying convergent. So let's establish why is this true. So generally we will consider the following. So let's say that Bn is An plus absolute value of An. Then what? Then we know that Bn is greater or equal to 0 because absolute value of An is greater or equal to An. On the other hand, it's less than or equal to 2 times absolute value of An. Because again, because An is less than or equal to absolute value of An. And then what happens? Now Bn itself is a positive, so it's a member, so it's a series, so some Bn has positive members. And it's dominated by a convergent positive series. Sum of 2 absolute value, right? So it is convergent. By the way, I assume that, but I didn't put it on the board in the proof. Assume sum of absolute value of An converges. We better have it on the board that we know. So that's where I called it 2, of course, doesn't affect it. Yes, but Bn is convergent. Why is that An convergent? Because from here we have that An equals Bn minus absolute value of An. So then sum of An equals sum of Bn's. If they converge, but they do converge, we know both, minus sum of absolute value of An. Since they both converge, then sum of An converges. So here it is. So generally what happens, and that's actually what we always do when we look at the series that's where the members switch sign. So the first thing that we want to know is how the series of absolute values behaves. If we get convergence there, we're done. So then it is convergent in the standard, in the just standard way of convergence. But what could happen is that the series is convergent itself, but the absolute value series is not convergent. When that happens, we say that the series is conditionally convergent. So let me squeeze it in here. Sigma An is conditionally convergent. If sum of An and goes to infinity converges, but the sum of absolute value diverges. So that's like a weaker version of convergence. By the way, about my comment that sometimes when you reshuffle series where the members switch sign, you can run into troubles that actually the sum changes. If it's absolutely convergent, that's not going to happen. All these strange things happen with conditionally convergent. So that's a very much weaker type of convergence. So whenever you have, once again, series where not all the members are positive or all the members are negative. I never mentioned that. If all the members are negative, that's the same as all members are positive because pull out minus and everything works the same way. So if the series switches sign, then the first question is test for absolute convergence using the positive test and then see what happens. A couple more examples. example, consider sum of negative 1 over n plus 1 over n equals 1 to infinity. We just analyzed this series a minute ago. We said it's Leibniz series, so it's convergent. No, I don't even want to talk about it. Why? Because first thing, when you see a series like this, you first test absolute convergence. So we test sum, and it goes 1 to infinity. Absolute value of this plus or minus 1 is just 1. We get 1 over. We actually get harmonic series. So diverges. So no absolute convergence. Do we still have chance for conditional convergence? The answer is yes. Absolute convergence, no. Now conditional. And then you remember from a minute ago, we established this in a previous example. So, sum minus 1 over n plus 1 over n is conditionally convergent. Here it is. All right. Let's see a couple of examples that are just bulkier, but basically nothing really dramatically different. So here it is, number 58. Sum n goes 0 to infinity, negative 1 over n over square root of n plus 4. So just check the convergence. Check the convergence. We check for convergence. So what we said is first thing is we check absolute. Because why? Because if I get yes on that, I don't need anything else. So absolute, I look at the sum and it goes 0 to infinity, 1 over square root of n plus 4. It's quite obvious that this is divergent because this 4 cannot do a big thing. 1 over root n is just by the p-test, p is 1/2, so it's divergent. More writing, so compare with the sum of 1 over root n and it goes 1 to infinity. So we do limit, and it goes 1 over root n plus 4 over 1 over root n, which will be, when you take a reciprocal, root n over root n plus 4, which will be limit when n goes to infinity. I'll divide by root n, so I get 1 over 1 plus 4 over root n. Obviously, this approach is 0, limit is 1. So since limit is finite and not 0, then we know that they are equiconvergent since by the p-test, p equals 1/2, sum of 1 over root n is divergent. The sum of 1 over root n plus 4 is also divergent. So that would mean that our series is not absolutely convergent. Doesn't have superconvergence. Does it have that weak convergence? Let's see. What about conditional? So our only tool for conditional ones is actually sometimes if it's geometric series with negative r's, we can use that sometimes. But our main tool is actually our alternating series test, because this is alternating series. So we want to C, so let's look at n equals 1 over root 10 plus 4. And we need to check what? If we limit an itself, so are the drops small to pass divergence test if we don't do that, of course. And that's true, because it's really when we get 0. It's 1 over infinity, so we get 0. So that's good. Is it decreasing? Obviously, yes. Why? Because what? Square root of n is increasing. We don't need any argument, that's just common sense. The bigger n, the bigger the square root. Or, if you want, you can draw the graph. Looks like this. Then what? Square root of n plus 4 is increasing also. Because when you add 4 to bigger number, again. But then what? When you take reciprocal on positive numbers, 1 is decreasing. So what then? I want to write on this line because you might not see it well. So here is conclusion. According to alternating series test, the series is conditionally convergent. Because we showed that absolute conversion has failed, conditional work, so this is the conclusion. And just one more problem, and that's it for this section. Fairly similar. Might be a little trickier to see. Oh yeah. So here it is. Some example. The sum, and it goes 0 to infinity, it doesn't matter. -1 to the n. Actually, that's when it's nice when you start from 0, then you don't need n plus 1, because usually we like to start with a positive. 3n squared plus 5 over n to the 4th minus 7n squared plus 5. So what about this one? You can see it right there without even touching the problem that this has super convergent. This will be absolutely convergent. Why? Because look how small. So forget this, just size of the members. They are very small. Why? Because we have a square here, we have 4. So bottom dominates by 2. Basically, this guy will absolute values will behave like hypergeometric, so they will converge. So that's our plan. We cannot just write that, of course. Yes, but that tells you when you just look at the problem, it just sends you a good message. So what are we going to do? So first, check for absolute convergence. So we are checking sum of 3n squared plus 5 n to the 4 minus 7n squared plus 5. And here goes 1 no 0. So what happens here? Actually, you know what? There is a little trouble here. Not really trouble, but if you want to do problems nicely, you have to be careful about those things. I don't know, to have a clean solution. What happens here? Usually we say, oh, this is a positive number and then this is alternator. But look, when n is 0, that's all good. But when n is 1, what do we get here? 1 and 5 is 6. 6 minus 7 is -1. So this number is actually negative. So you don't have alternation in the beginning. But it's quite easy to see that starting from what n equals 2, it will be negative as well. Starting from n equals 3, so this is greater than or equal to 0 for n greater than or equal to 3. So generally I can do the following. All right, instead of from 0, I will check it from 3 to infinity, because I told you first few members are just 3 numbers, so they affect the result, but not the status of the convergence. So let me analyze this one. So now everything is positive. How do I know that? Because when n is greater or equal to 3, then we have here n squared times n squared minus 7 plus 5. So this is greater than 0, so it's all good. Anyway, so what do I do here? I'll compare it with some 1 over n squared when n goes 3 to infinity. I know that this one is convergent, p-test. P-test. P equals 2 is greater than 1, so it converges. And then, let me erase this, I take a limit. When n goes to infinity, 3n squared plus 5 over n to the 4th minus 1. And I divide by 1 over n squared. And what will that do? It will balance the powers or get a limit. That's all straightforward. So when I multiply by n squared, I'll get 3n squared plus 5 times n squared over 1 over n to the 4th minus 7n squared plus 1. I really dislike the idea to use the L'Hopital rule here because it's so basic that there's no need. So I'll get what? Bring this here to be more patient. So when I divide by n squared, what do I get? We then to the 4th, right? 3 plus 5 over n squared over 1 minus 7 over n squared plus 5 over n to the 4th. And then what happens? This goes to 0, this goes to 0, this goes to 0. Our limit is 3. And that's it. We got finite limit different from 0, so they are actually convergent. Since measuring stick is convergent, and our series is also convergent. Actually, absolute value of our original series. So then our series is convergent in this strong way, we say. So our series is absolutely convergent. And that's our final conclusion.